NEC Section 450.3 requires a main circuit breaker, or MCB, for a transformer secondary where the load exceeds 2500 kV or the current rating of the transformer exceeds 4000 amps. However, NEC Section 384.18 allows for the omission of an MCB for transformer secondary feeders that are protected by a high resistance granted neutral, or HRGN, system. Considering a 2500 kV amp transformer with a 4000 amp secondary bus and an installed HRGN system, the criteria to omit the MCB based on the NEC requirements are met. A vendor might express concerns about potential safety hazards without an MCB. Specifically, without an MCB, a fault on the secondary bus could cause a large current surge, potentially damaging the switchgear. To mitigate these concerns, several measures can be considered. Firstly, install an additional overcurrent protection device such as a current limiting fuse in series with each feeder breaker. Secondly, implement a rigorous maintenance program to ensure the integrity of the HRGN system. Thirdly, have a written safety plan in place for working on the secondary bus with the MCB removed. The HRGN system limits the ground fault current to a low level, typically 5 to 10 amps. This low current minimizes damage to equipment and reduces the risk of arc flash. Without the HRGN system, a ground fault could result in a very high fault current, potentially causing significant damage. The purpose of the HRGN system is to limit the ground fault current, not to eliminate it entirely. It is essential to coordinate the overcurrent protection devices with the HRGN system to ensure proper operation. The ground fault relay associated with the HRGN system should be set to trip at a current level below the maximum ground fault current that the HRGN system can handle. Coordination studies are essential when designing and implementing overcurrent protection systems. These studies ensure that the overcurrent protection devices operate in a coordinated manner, minimizing the extent of an outage. Without proper coordination, a fault on one feeder could cause multiple breakers to trip, resulting in a widespread outage. Furthermore, regular testing and maintenance of the HRGN system are critical to ensure its continued reliability. The resistance of the grounding resistor should be checked periodically to ensure that it is within the specified range. Additionally, the ground fault relay should be tested to verify its proper operation. Safety plans should outline the procedures for working on the secondary bus with the MCB removed. The plan should include steps to energize the equipment, verify the absence of voltage, and ground the conductors. Employees should be trained on the procedures outlined in the safety plan. Moreover, consider using current limiting fuses in series with each feeder breaker. Current limiting fuses can interrupt fault currents faster than circuit breakers, reducing the amount of energy released during a fault. This can help to protect the switchgear from damage. Remember that documentation is very important. Keep detailed records of the design, installation, testing, and maintenance of the overcurrent protection system and the HRGN system. This documentation can be valuable for troubleshooting problems and for demonstrating compliance with applicable codes and standards. The absence of the main circuit breaker necessitates careful consideration of alternative protection strategies. The HRGN system offers a specific type of protection focused on ground faults. Other potential fault types such as phase-to-phase faults or bolted three-phase faults require adequate protection from the feeder breakers and any supplementary overcurrent devices. The coordination between all these devices is of the utmost importance. A short-circuit study should be performed to determine the available fault current at the switchgear. This study informs the selection of appropriate interrupting ratings for all breakers and fuses. The interrupting rating must be sufficient to safely interrupt the maximum available fault current. The prospective short-circuit current can be calculated using impedance data from the utility transformer, conductors, and other equipment in the system. Software tools are available to aid in these calculations. Moreover, consider using a combination of fuses and circuit breakers to provide optimal protection. Fuses can provide fast current limiting protection for high fault currents, while circuit breakers can provide overload protection and switching functions. The selection of fuses and circuit breakers should be based on the specific application requirements. Remember that personal protective equipment, or PPE, is always necessary when working on or near energized electrical equipment. The PPE should be selected based on the potential hazards, such as arc flash. An arc flash hazard analysis should be performed to determine the required PPE level. This analysis considers factors such as the available fault current, the clearing time of the overcurrent protection devices, and the working distance. Furthermore, regular training on electrical safety is essential for all personnel who work on or near electrical equipment. The training should cover topics such as arc flash hazards, lockout/tagout procedures, and the proper use of PPE. The specific requirements for overcurrent protection can vary depending on the applicable codes and standards. In addition to the NEC, other standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, may also be applicable. It is important to consult with a qualified electrical engineer to ensure that the overcurrent protection system meets all applicable requirements. When adding overcurrent protection, consider the impact on selective coordination. Selective coordination ensures that only the overcurrent device closest to the fault opens, minimizing the extent of the outage. Without selective coordination, a fault on one feeder could cause multiple breakers to trip, resulting in a widespread outage. Selective coordination studies are essential when designing and implementing overcurrent protection systems. These studies involve analyzing the time current curves of the overcurrent protection devices to ensure that they operate in a coordinated manner. Software tools are available to aid in these studies. Furthermore, consider the impact of the added overcurrent protection on the system's reliability. While overcurrent protection is essential for safety, it can also reduce the reliability of the system if it is not properly designed and coordinated. For example, if the overcurrent protection devices are set too sensitively, they may trip unnecessarily, causing nuisance outages. It is important to strike a balance between safety and reliability when designing the overcurrent protection system. Remember that overcurrent protection is only one aspect of a comprehensive electrical safety program. A comprehensive electrical safety program should also include elements such as arc flash hazard analysis, lockout/tagout procedures, and regular training on electrical safety. The specific requirements for an electrical safety program can vary depending on the applicable codes and standards. It is important to consult with a qualified safety professional to ensure that the electrical safety program meets all applicable requirements. The installation of a high-resistance grounding system introduces some unique considerations for ground fault detection and protection. The ground fault current is intentionally limited to a relatively low value, often a few amps, to reduce fault damage. Traditional overcurrent protection devices may not be sensitive enough to detect these low-level ground faults. Therefore, it's common to use a ground fault relay specifically designed for high-resistance grounded systems. This relay monitors the neutral current and trips when it exceeds a preset threshold, typically a few amps. The location of the current transformer, or CT, used for ground fault detection is also crucial. It is typically placed on the neutral conductor between the grounding resistor and the neutral point of the transformer. This ensures that the CT sees the entire ground fault current. The setting of the ground fault relay should be coordinated with the withstand capability of the grounding resistor. The resistor is designed to withstand the limited ground fault current for a certain period of time, usually 10 seconds. The relay should trip before the resistor's withstand time is exceeded to prevent damage to the resistor. Additionally, a high resistance grounding system can introduce transient overvoltages during ground faults. These overvoltages are caused by the inductance of the system and the sudden change in current. Surge arresters may be required to protect equipment from these overvoltages. The selection and placement of surge arresters should be based on a transient overvoltage study. Remember that the high resistance grounding system does not eliminate the need for equipment grounding. All non-current carrying metallic parts of electrical equipment should be properly grounded to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protection devices will operate properly in the event of a fault. The grounding conductor should be sized in accordance with the applicable codes and standards. Furthermore, consider the potential for sympathetic tripping of ground fault relays. If multiple high-resistance grounded systems are connected to the same electrical system, a ground fault on one system could cause the ground fault relays on other systems to trip. This can be avoided by carefully coordinating the relay settings and by using directional ground fault relays. Directional ground fault relays can distinguish between faults on the protected system and faults on other systems. They only trip for faults on the protected system. The use of a high-resistance grounded system can also affect the selection of cable insulation. The cable insulation should be rated for the maximum voltage that can occur during a ground fault. This voltage can be higher than the normal operating voltage. It is important to consult with the cable manufacturer to ensure that the selected cable insulation is suitable for use in a high-resistance grounded system. Also, the location of the high-resistance grounding resistor is important. The resistor should be located as close as possible to the neutral point of the transformer. This minimizes the impedance between the resistor and the neutral point, which helps to reduce transient overvoltages. The resistor should also be protected from the environment. It should be installed in a weatherproof enclosure to prevent damage from moisture, dust, and other contaminants. Furthermore, consider the potential for harmonics in the electrical system. Harmonics can increase the ground fault current and cause the ground fault relay to trip unnecessarily. If harmonics are present, it may be necessary to use a harmonic filter to reduce the harmonic content of the current. The design and installation of a harmonic filter should be performed by a qualified electrical engineer. Also, the high-resistance grounding system should be inspected and tested regularly to ensure that it is operating properly. The inspection should include a visual inspection of the grounding resistor, the ground fault relay, and the associated wiring. The testing should include a measurement of the resistance of the grounding resistor and a test of the ground fault relay to verify that it is tripping at the correct current level. The inspection and testing should be performed by a qualified electrical technician. The documentation for the high-resistance grounding system should include a detailed description of the system, including the location of the grounding resistor, the type of ground fault relay, and the settings of the relay. The documentation should also include the results of the inspection and testing. This documentation can be valuable for troubleshooting problems and for demonstrating compliance with applicable codes and standards. In summary, the decision to omit the main circuit breaker and rely on a high-resistance grounded neutral system requires a thorough understanding of the applicable codes and standards, as well as careful consideration of the potential safety hazards. It is important to consult with qualified electrical engineers and safety professionals to ensure that the system is designed, installed, and maintained in a safe and reliable manner. Additionally, a comprehensive electrical safety program is essential for protecting personnel from electrical hazards. Remember that electrical safety is a shared responsibility. Everyone who works on or near electrical equipment should be trained on the potential hazards and the proper safety procedures. By working together, we can create a safe and productive work environment.